Now the thing that we're doing right now, so I'm gonna reiterate this for the video. So we're taking a microwave transformer, and we are reading the voltage that's coming off of the small secondary winding. The small secondary winding on a microwave transformer is this little winding that's the small winding. It's this little winding right here that's right between the primary and the secondary. And the hopes is that I could actually use that as a trigger winding in an Armstrong oscillator. And that's what we're going to find out now. I need it to be below like 20 volts. So if I can get below 20 volts out of this, then this will work for an Armstrong oscillator. So that's what we're going for here. All right, now I have my thing set up here. And we're going to go that what you have to be careful with if you're going to do this at home, what you really have to be careful with is, whilst this is low voltage, it's very high current, because we are stepping down the voltage, we're stepping up the current. On a transformer, the voltage and current are inverse. So whenever you step the voltage down, you raise the current. Whenever you step the voltage up, you lower the current. That's just how transformers work. Alright, so I'm going to hook up the mains voltage. It's actually a little more loaded than I thought it would be. And it does not why is that? I guess because the magnetic induction. And I'm not getting much of anything. So let me adjust this. Let me adjust the trigger here. Trace. That is trace 1. And let me change it from 400 volts to 100 volts. All right. And now let's see what she got. Oh, now we're getting somewhere. What do we got? 6.7 volts. That's actually something we can use. I can take this a little more. Trace 1. Let's go to 50 volts, actually 20 volts. Yeah, because that puts the 6 volt range right up here. Alright. And there it is. That is actually an odd waveform. And I wonder if it's not because of the magnetic shunts that are between the coils of the primary and secondary. That is an odd waveform. I actually kind of want to know what my amperage is right now. But the way I've got everything set up, I can't do that. So here's the thing though, let's do some math. I got a max of what, 5.4 volts? So a max of 5 volts. Oh, I know why that's doing that. You know what I want to do? I want to see what our waveform looks like when I actually load this up, because we may be getting flyback voltage back into the power supply. I'm not sure if that's a thing on the AC, but it could be. So let's see. If I do some math, then let's see, 5 volts. Let's see if I just do some math. Just do a little bit of math over here. Oh, of course, everything's going to fall because this is just an unmitigated mess. Calculator. Alright, so what is that? 120. Well, 163 divided by 6. We'll just go 6. So that's 27 times. So if I have 1 amp, then I'm going to be putting out 27 amps. But here's the thing. If I load this up, my limit is the 15 amps that I can get through this circuit. Yeah, that would be toasty. That would be very toasty. So, 5 volts. Well, 5.4. I think I can use that. That might actually be a bit too low, believe it or not. That might actually be a bit too low. But it is something that I can work with, for sure. So if I use that as a trigger, now here's the other thing I wanted to do. I wanted to measure these together, and I'm just thinking of how I can do that. Just trying to figure, because I left my freaking clamps downstairs like an idiot. Ooh, I have an idea. I have an idea. Ladies and gentlemen, I have an idea. Alright, we're doing that on the mains. And we're going to use our smaller pocket scope on the small one, on the other line. Now, I do have to be careful with this, because if this shorts together, that's a lot of amperage. And all that amperage equals a lot of heat, and that's a giant no-no. So definitely can't short it, and hope the resistance, the resistor inside this thing is up to the party. Alright, so I got 5 volts. I could actually lessen that. I want my position. To be up higher, because we are going to be doing AC. Alright, I think that's it. Alright. Ooh. Oop. Forgot to change that back. Yep, look at that waveform. It comes up real nice and pretty on that. That actually works out quite nice. Trace 1. Need to change that back to the 400 volt. Alright, that does not change. That does not change. And again, we got to be very careful of that high voltage line right there. But yeah. Alright, so I'm at 2 volts per division. So 2, 4, 5 volts-ish. Yeah, that's about right. I don't know if you guys can see the pocket scope very well. Probably not. But because that's kind of a crappy scope, but for $80 it works pretty well. Especially considering this one cost $10,000. So there it is. There it is. So we have our sine going in, and we're getting like 5+ voltage coming out. Coming to think of it, I actually kind of want that to be a bit higher. So what I may actually do is either get it closer. So there's several magnetic shunts between the primary and the secondary coil, so I may want it closer. That would make a difference. And I may want to add a couple windings in there. Also, it doesn't have to be such heavy gauge, but I may want to add a couple windings in there to get the voltage closer to like 10. So if I theoretically, if I double the windings that this coil is doing right now, then I should be able to get closer to like 10 volts, probably 12, which is a very usable number in electronic circuits. At that point, then, it literally just uses the sine wave right here that it produces. And let's see if I can adjust the sweep to show this a little better. Alright, seconds division. Ooh, too much. There we go. Um, yeah, it's got an interesting waveform. It really does. It's a stepped waveform, which I do not understand it, but whatever. It's probably because of the principles of the transformer. But that is something that I should be able to use. That really throws a spark. We like sparks. All right. So that confirms that. The thing is, I don't know if that's what we really want. I mean, that would so an Armstrong oscillator theoretically. Now, mind you, there's a capacitor involved. So this is a couple things that I've learned about electronics in the past few days. Is when it comes to coils of wire, which are inductors. So when it comes to inductors, if you take an inductor which stores, this is crazy. This actually gets very crazy, very in depth. But if I take, in the world of electronics, there are quite a few different voltage generators or voltage storage devices. There's a little bit of a difference between the two, but for the sake of not being complicated, we can say that that there's not that much of a difference. Yes. Actually shut that down properly for once. Windows XP, everybody. Gotta love it. So, voltage differences. It turns out there are 3 ways off the top of my head that I can describe how to store electrical energy. One of them is chemical, like batteries. So a lead-acid battery stores potential electrical energy in the molecules and how they react with the different chemicals. Then there's capacitors, which store electrical energy based on electromotive, well, not electromotive force, but electrical force. In other words, an induced polarity across closely spaced conductors created by charging one plate induces a negative volt and inverse voltage on the other plate, and it's able to store energy that way. Then the other way to store energy is magnetic force, which is what transformers do, or inductors. Like these things right here. I should probably unplug that before I just go grabbing up on it. That was almost an electrocutable event right there. It's only 110 volts. It just tickles a little bit. So these joints right here, these are called inductors, and they essentially store and release magnetic energy. Well, they store electricity in the form of magnetic energy and then release it at a certain rate, and that rate is dependent on the collapse of a magnetic field. So it's interesting stuff. But transformers have a lot to do with that, because they are a giant coil of wire. And so there's this thing where if you take an inductor, which stores energy in magnetism, and then you take a capacitor and you marry the two, it's called a tank. Like T-A-N-K. It's called a tank. And what happens if you charge it correctly, then it creates a self-oscillating circuit. In other words, the voltage in the energy stored in the inductor, magnetics, will actually discharge into the capacitor, and then the capacitor stores the energy, and when it reaches its peak, then the resistance, the inductive resistance of the coil collapses, and the capacitor discharges through the coil the other direction, and it literally just goes back and forth between the inductor and the capacitor. Given that there were no parasitic resistances, that would just do that forever. But this is the real world, and parasitic resistances are involved in wires, the resistance of capacitors, the resistance of the coil of wire. They all rob that energy, so it doesn't last forever. But what you have to do to make that reaction last for a while, so you take that reaction and you tune the capacitor to the inductor so that they reach resonance. Resonance being the optimal frequency for the inductor to operate at. And again, that has to do with how fast the magnetic field builds and collapses. So you tune your capacitor to the inductor, and then in order to keep that going, overcome the resistance, the residual resistance within that circuit, in order to keep that going, you induce voltage, or you add voltage every once in a while in the circuit. And that's what an Armstrong oscillator does, is it uses a trigger coil to trigger a switch transistor to charge the capacitor on the off cycle of the capacitor, so that at one point in that cycle you have both a power source and the inductor charging the capacitor together, and all you have to do is add a little bit of energy to that circuit, and then it stays oscillating, and it uses the trigger coil to know when to actually charge, to add charge to that circuit. And then you just use the magnetic frequencies off the other end of the transformer, off the secondary winding, to produce your voltage. That's an Armstrong oscillator. And the thing is, that should be a self-tuning oscillator. In other words, it's going to reach, given the right capacitor is selected, it's going to reach resonance frequency and stay there. So you don't have to do any regulation of that. Now, I've been thinking to myself, like, is that what I want? Technically, resonance frequency on a transformer, operating at resonance frequency, is the best possible outcome, the most efficient operating parameter for the transformer. So you're going to get the most energy through the transformer without causing problems. However, it may be too fast, and that circuit only works for that transformer. So I'm not sure if that's really actually what I want to do, but I think it may be interesting. I do believe it may be interesting to try and use that oscillating circuit to basically, I guess, reach the maximum potential of a given transformer and see what it can do. And the entire point of it altogether is to say that at 60 hertz I can get so many amps through this transformer. But if I run at resonant hertz, whatever that resonance may be, it could be 400, it could be 600, it could be 300, you know, because the iron core, it's not going to be in the thousands, but like if it were a ferrite core transformer, the resonance frequency could be in the several thousands of hertz, and at that point you're going to transfer a lot more energy through that transformer than you would at 60 hertz. So it's basically the possibility of using one transformer to do the work of 2, possibly 4 transformers the same size, running at 60 hertz. All in a nutshell, it's the idea of using science and electronics to tune the transformer so that it can operate as a welder and do more with a smaller package than all the rest of the microwave transformer welders out there do at just 60 hertz. That's the whole nutshell idea of all of this. The crazy idea is to make a welder out of this microwave transformer that can outperform everybody else's microwave transformer welder out there, so that I can then say I have the best microwave transformer welder on YouTube. That's the idea. Maybe I shouldn't say that, actually, because then somebody else will beat me to it. Lord knows everybody else has more resources, but whatever. That's the idea, so that's what we're going with.